Welcome, this is lecture number 55. In this lecture, we are going to talk about small signal and large signal based tuning and their comparison using MATLAB simulation. So, here we will first talk about small signal based design and tuning of voltage mode and current mode control in a buck converter. Then we will talk about large signal based tuning of voltage mode and current mode control, that means both are in buck converter. Then we will talk about small signal based tuning of voltage mode and current mode control in a boost converter, and then finally large signal tuning in a current mode control boost converter. So, if we recall, I am not going to again, because we have already discussed the tuning methodology small signal as well as large signal in sufficient detail. So, first in the buck converter we will take a voltage mode control, current mode control, both are designed using small signal model. Then in large signal model we have designed both current mode and voltage mode control. So, if you recall our voltage mode control design, so this is the loop transfer function that we have discussed multiple time. You will get more detail in lecture number, if you go to lecture number 34, 35, both have like a extensive design. For type 3 compensator, I think you have to go for lecture 35. So, details are available. So, here the GVD is given, and if you are considering alpha term, if you are considering alpha to be almost equal to 1, then it is simplified to ESR 0, and if we take omega 0 to be 1 by square root of LC, because the R plus RC by R plus RL, RE both are more or less same. So, we have approximated, and that we have discussed, and Q factor also. So, this is a transfer function, and we need a type 3 compensator, that we have discussed. And then how to change for exact perfect compensation by analytical pole 0 compensation. We know we can cancel one controller pole to cancel ESR 0, one controller, another controller pole is flexible, and the controller zeros are placed to cancel the control to output transformation pole. Okay. And then we know that how to obtain this omega p, which is nothing but our flexible controller pole, and that required two information. We need to provide what is my crossover frequency, and generally we take up to 1/10 of the switching frequency, and then we need to specify the phase margin, and we have discussed detail model matching and all. And we know the controller gain will turn out to be the ratio of omega c by omega p, where omega c is the crossover frequency and omega p is the pole frequency that we will obtain from this equation. And we have already discussed multiple times the block diagram, MATLAB diagram of the voltage mode control, which we are not going to discuss again, right. And again in this voltage mode control we are setting the compensator. This is our GC controller, type 3 compensator that we are setting from our MATLAB code, and we know how to design. If it will ask for phase margin, it will ask for phase margin as well as gain crossover frequency, and then buck converter you will have a two flexible choice, right, and you need to provide the RAM in order to find out the controller gain. Then for the current mode controller design in a buck converter, if we recapitulate, our loop transfer function takes like a first order system, and then we need to take the controller which is a type 2 compensator. It is like a type 2 compensator that we have discussed into, I think it is lecture number 38, we discuss in sufficient detail. So, you will find lecture 38, okay, where omega Cz, omega p, omega Cp, omega ESR all are discussed, how to place the controller 0 and controller pole, because we have one controller 0, one controller pole that we have to cancel, and the another pole is at origin. So, you will get a first order system, right, and how to get Kc, the controller gain, that we also discussed. And we have also discussed the MATLAB model under current mode control. This has been we have discussed multiple times how to implement current mode control buck converter. And here we are also considering an additional current feedback loop, load current feedback, feed forward. Either you can put it 1, then it will be a load current feedback, and if you set to 0, then there is no load current feed forward. Okay. So, in regular current mode control we have discussed in lecture 38, what we have discussed, that if you do not consider load feed forward, then the current mode control performance is sluggish. But if you consider load current feed forward, then you can make the output impedance close to 0 but there will be some finite slew rate due to the characteristic impedance. But if you talk about reference transient, because you are talking about the bandwidth, then you will find during the reference transient there will be hardly this gain, even if you do not consider, it does not matter. Okay. So, in a buck converter we are going to consider load transient performance. Okay. And then we also discuss in lecture number, I think lecture number 50, the PI controller tuning parameter of a buck converter, where Kp we discuss, where we have two separate gain for step up and step down, that we have discussed. And then we have said, we have also discussed that how to design this integral gain by means of small signal model, that also we have discussed in sufficient detail. And for load current feed forward, we need to consider normally load current gain to be 1 for buck converter, right. And we have also discussed and how to implement, it is a standard current mode control, that's just now we have discussed, and we are considering the load current feed forward. And if you take the PID controller for our large signal tuning, then we have to also discuss what should be my proportional gain and what should be my VQ for step up and step down. We have discussed in sufficient detail in lecture number 50, and then how to set the integral gain from the small signal model. Then the derivative gain is simply the capacitor value, and then we need to put a band limited derivative. Because of this band limited derivative, the time constant should be much smaller than the switching period, that we have also discussed. And we know the voltage mode control implementation, output voltage, reference voltage. So, it is exactly same as the regular voltage mode control, where we are only applying the large signal tuning. Okay. So, let us go to the simulation model and check our the performance comparison. So, if we go to the simulation model, we are applying a load step of 20 ampere. Okay. And there is no, so we already discussed in our time how to develop interactive simulation case study. And if we run this file, suppose if you want to run it, then undefined. So, yes, so it will ask for, you need to change the MATLAB. Okay. So, let us first wait, because we will go one by one. The first thing, it will buck converter parameter, it is the same parameter file that we have been discussing throughout this lecture, there is no change. Next, we are considering 5 millisecond total simulation time, 3 millisecond time, we are applying a load step transient. Now, initially what we are considering, okay, comment, our traditional, we can go for a PID controller also, or traditional PID controller. Let us go for a traditional PID controller, where if we run it, it will ask for bandwidth. So, let us say we know that PID controller, if you go for 1/10 of the switching frequency, then the model may not be valid. So, you can make it like a like a 500 kilohertz is the switching frequency. So, you can set, let us say 25 kilo, 1/20th of the switching frequency, and let us check how does the response look like. So, response is not at all good, because it has a large overshoot undershoot, and which is not acceptable. Okay. We can improve the response by increasing the bandwidth. So, you can set, let us say 100 kilohertz or sorry 80 70 kilohertz, but model may not be valid, but we can so we can reduce it, but the question is the model validity remains a question. So, that is why the PID controller will not talk, because the very sluggish response, even if you go up to 1/10 of the switching frequency, if we go, then even the response is not satisfactory. We will hold it the result, this is using PID controller in small signal model. Now, on top of this, let us say if we use a red color, we are going for a type 3 compensator. Okay. So, type 3 compensator, where we are considering, now this we have already run comment type 3, this is our type 3 compensator. So, uncomment, now we are running. So, you need to hold this. Okay. So, run it. Here we are going to, like, it can go up to 70 to 80 kilohertz for load transient response, the model still matches fine, and band gain phase margin 60 dB. So, let us see how does the response look like. is this response is much faster because model validity works even for a wider frequency range, but still this may not be sufficient. Now, we are going for large signal based tuning and we are using another color, let us say we are using magenta or maybe we can use green color for the large signal based tuning, where we will comment this particular file, we will comment and we are going for large signal based PID controller tuning, uncommon. So, here this function is calling PID controller where all the gains are set accordingly, and I have shown you all the expression as well as the block diagram. So, it is simply run it, let us run it and check how does the response look like. You can see the response is drastically improved because the green color, it is just around 100 millivolt is the transient response, your undershoot less than 100 millivolt, and the recovery time is just a few cycle. I mean it is like a, because it is just a 2 switching cycle, whereas this takes much longer duration. And if you go to inductor current, you see the inductor current is not very significantly high, but our traditional approach of designing because of the model validity and small low duty ratio. So, you will see the difference will come at the fast recovery time, because since the small signal require low duty ratio perturbation. So, during the slew up process, there is a turn on off happening, and because of that it will slow down the transient response, whereas the large signal tuning, it allowed duty ratio saturation. You see it is turning on for quite some time and then turning off, and it is coming to next operating point in almost one switching cycle. So, it achieved almost time optimal recovery. So, now this large signal tuning can drastically improve the transient performance compared to the small signal tuning. Now, we are going for current mode control. So, let us close all the files and we will again clear once more. Now, we are going for current mode control. So, in current mode control, we will see two things. The first we will go for small signal based current mode control, uncomment. So, here KFF I have shown you. If you go to the KFF, if you go to current mode control, so this is a load current feed forward. So, if you set KFF to be 0, then you are not considering load feed forward. Okay. So, we will consider cases. First, KFF equal to 0. So, this case we are talking about, let us say we are using blue color. So, the regular current mode control design. Okay. So, let us run it, regular current mode control design. So, if you run it, it will ask for bandwidth. So, let us say we can go up to let us say 100 kilohertz, trying to go close to 1/5 for load transient, somewhat we can go, but I think this still model matching will be a concern, but we are trying to go close to 1/5. Let us see what happened. So, this is a load transient response using current mode control, and this is a response, and you see this we have discussed, the model matching will not happen due to the jump. So, we should not go to 1/5. So, let us limit our whole thing to 1/8. That means, we will get 500 by let us say 1/8. And if I say the response, so now there is no as such very large overshoot, fine. So, it is much sluggish response. Okay. But unlike in voltage mode, there is a overshoot undershoot, it has only undershoot, but it is slow. Now, if you consider on top of that load current feed forward, that means we are considering 1 and we are using a different color, let us say we are using red color, and let us run it. So, if you run it, we want to hold it, then so here also we are 500 divided by, so let us go 110, and see it is much faster because we have incorporated the load current feed forward, and we have discussed the load current feed forward can drastically improve the performance, right. Now we are going to large signal tuning, okay, for current mode, where we need to incorporate load current feed forward, and we discussed that we can use load, we can estimate the load current, or you can use a physical sensing, right. So, estimating load current is a good solution in digital control solution. So, let us do that and we will run it now using green color and see what happened. Yes. So, you see, when we consider our tuning, large signal tuning, it is recovering in almost 3 cycle, whereas load feed forward is taking some more time using the regular current mode control with load feed forward, and it is somewhat sluggish response. So, it takes few more cycle to reach steady state, okay. But it is good that both are giving fine with load feed forward, but optimal gain make it even faster, right. So, you can just check it here. So, these two are the response, there is no, but because of load feed forward, it is allowing the duty ratio to saturate. So, that, but in regular current mode control, because of on off operation, it is slowing down the transient performance, and which is quite obvious, and that we have discussed. So, we have discussed about PID tuning, large signal, small signal for voltage mode, current mode, all case study. Now, we are going to consider a boost converter. So, in a boost converter, we are going to consider reference transient using small signal as well as large signal. Okay. So, let us go. Now, we will just stop all this waveform. So, let us go to our boost converter case study. Okay. So, we have considered buck. Now, in boost converter, first we will consider a voltage mode control technique, where we are considering 1 ohm load resistance, 3.3 volt input, 5 volt output, and we are applying a load step transient of a reference transient of 0.2 volt. Okay. So, let us first run it, and we will use, let us run it. So, it will ask for FRHP, and we know for voltage mode we generally go for 1/5 of the RHP. So, let us do that. So, this is the 1/5 of the RHP using our, so this is blue color. Now, we are using same red color for current mode control. So, we will go to current mode control, we will hold it. Now, we will go for traditional current mode control, where we can go up to 1/3 of the RHP0. So, 1/3 of the RHP0 we can go, right, 1/3 of the RHP0 we can go, and let us check. Okay. So, I think we should change the color. So, we should change the color 1/3 of the RHP0, just hold on, we are redrawing this, we are okay. So, we have drawn one for voltage mode control and the other for current mode control, and these two are their inductor current. For voltage mode we took 1/5 of the RHP0, for current mode we took 1/3 of the RHP0, and it shows a non-minimum phase behavior. Now, we are going for large signal based tuning, where we will disable the small signal tuning comment, and we are going for large signal tuning. And as I told, for large signal tuning, the voltage can be derived using the expression. So, if you go for that, so let us first derive in voltage mode control. We know how to discuss, how to derive the gains, and we have discussed in lecture number, I think 36. We have discussed in detail different parameter of the open loop plant. Then for the PID controller design, what will be the optimal PID gain, K1, K2, these are here K1, K2. Then tau d is a band limited derivative we are considering, integral gain, this will require the crossover frequency, and from here we are getting all the controller gain that we have discussed. And we know that how to implement current mode control, we have also discussed, that means there is a ESR0, RHP0, and we can go to type 2 compensator design, and the design parameter we have also discussed how to set, that means we have to take omega c by omega RHP, and that we are taking like a 1/3, that means we are taking 1/3, and this will compute the gain that we have derived. For large signal tuning, we know the expression, and as I told, the expression is somewhat is not very complex somewhat. So, we have computed this value. This is for load transient, we can also do for reference transient. We have computed this value and those values are plugged in into this MATLAB code, and we are comparing. Now, we are using a different trace. So, we are using green color trace, and we are using now our large signal based tuning. So, in large signal based tuning, you will find that it is reaching in one cycle, but there is a problem. The response is very fast, but unlike in buck converter where the time optimal control also achieve minimum voltage undershoot, but here the voltage undershoot drastically increases because your on time is large, and if you go to the current waveform, you will find you have a high on state on time because the current is increasing, and as a result of a longer on time, your voltage will simply fall. So, while it achieves very fast transient response, it is in reaching in 5 switching cycle, compared to much faster than your voltage mode and current mode, but it comes with this price. But we can always set a current reference. So, if you go to current mode control, if you go to our current mode control, we can always set a current reference. So, this current reference Imax that we are setting from the MATLAB file, and if you go to the MATLAB file, so this Imax we can reduce this Imax value. Okay, so let me check Imax. So, here it is 15 ampere, let us say we make it 12 ampere. So, we are setting a current limit, we want to rerun it, and now we are using black color, let us say black dotted color, dash color. So, if we want to set a current limit and run it, and let us see what happened, because now we are putting a current limit. So, once you set a current limit, you see the inductor current is reduced to 12 ampere because we can set according to our current rating, and the response is still much faster than both this control technique because it is taking few more cycle. Earlier it was just taking 5 cycle, but now it is taking 10 cycle, but it is faster compared to our traditional current mode and voltage mode control, because you can see. So, this black one is reaching much faster, right. See, so that means it is much better than, and we will show you in the subsequent lecture with the experimental result we have. That means with optimal tuning using linear control, then with optimal tuning, we have compared the optimal tuning with a linear controller tuning, then we also set a current limit, and we want to show that all these responses much faster than what we can achieve using small signal based tuning. So, in summary, we have discussed small signal based tuning of voltage mode and current mode control in a buck converter. We have discussed large signal based tuning of voltage and current mode control of buck converter. We have discussed the large signal and small signal. We have discussed small signal based tuning of voltage mode and current mode control in a boost converter, and we have compared the large signal based tuning of current mode control in a boost converter with and without current limit, and we saw the large signal based tuning can significantly improve the transient performance of DC-DC converter compared to small signal model. So, with this I want to finish it here. Thank you very much.